Welcome back to a new session of the MOOC on information security. The topic for discussion is cryptographic hash functions. The objectives of this module are to give an introduction to cryptographic hash functions and to understand the categories of hash functions. A cryptographic hash function is an algorithm that takes an arbitrary amount of data input referred to as a credential and produces a fixed size output of enciphered text called a hash value or just hash. That enciphered text can then be stored instead of the password itself and later used to verify the user. More commonly, message authentication is achieved using a message authentication code or MAC, also known as a keyed hash function. Typically, MACs are used between two parties that share a secret key to authenticate information exchanged between those parties. A MAC function takes as input a secret key in the data block and produces a hash value referred to as the MAC. This can then be transmitted with or stored with the protected message. If the integrity of the message needs to be checked, the MAC function can be applied to the message and the result is compared with the stored MAC value. An attacker who alters the message will be unable to alter the MAC value without knowledge of the secret key. Note that the verifying party also knows who the sending party is because no one else knows the secret key. Note that the combination of hashing and encryption results in an overall function that is in fact a MAC. That is, encryption is a function of a variable length message and a secret key, and it produces a fixed size output that is secure against an opponent who does not know the secret key. In practice, specified MAC algorithms are designed that are generally more efficient than an encryption algorithm. Certain properties of cryptographic hash functions influence the security of password storage. They are non-reversibility or one-way function. A good hash should make it very hard to reconstruct the original password from the output or hash. Diffusion or avalanche effect. A change in just one bit of the original password should result in change to half the bits of its hash. In other words, when a password is changed slightly, the output of enciphered text should change significantly and unpredictably. Determinism. A given password must always generate the same hash value or enciphered text. Collision resistance. It should be hard to find two different passwords that hash to the same enciphered text. Non-predictability. The hash value should not be predictable from the password. Cryptographic hashes take the plain text password and turn them into enciphered text for storage. Attackers who access your database are forced to decipher those hash values if they want to exploit them. In other words, hashes slow down attackers. Simple cryptographic hashes can slow down attackers, but ultimately attackers will be able to overcome them. Attackers equipped with fast hardware can easily crack hashed credentials. Good hash algorithms are designed to be collision resistant, but collisions are impossible to eliminate completely. MD5 and SHA-1 have been proven to contain non-collisions, that is, produce the same hash value from different credentials. Rainbow tables are optimized lookup tables that can be used to reverse engineer one-way hash functions. A rainbow table is basically a pre-computed set of plain text strings and their corresponding hashes. Large rainbow tables are publicly available, and attackers can use one of these tables to retrieve clear text data that has been hashed. There are a variety of cryptographic hashes that can improve your hash function and provide a greater barrier against attacks. Some of them are salted hashes. Salting adds random data to each plain text credential. The result is like two identical plain text passwords which are now differentiated in n-cipher text form so that duplicates cannot be detected. Keyed hash functions. A keyed hash function, also known as a hash message authentication code or HMAC, is an algorithm that uses a cryptographic key and a cryptographic hash function to produce a message authentication code that is keyed and hashed. Adaptive hash functions. An adaptive one-way function is any function that is designed to iterate on its inner workings, feeding the output back as input in a manner that causes it to ultimately take longer to execute. It is adaptive because the developer can adjust how much iteration to occur. To protect stored passwords, architects have applied the adaptive design to hash functions. The role of cryptographic hash functions. Cryptographic hash functions provide obstacles to attackers like speed breakers on road slowing down a speeding vehicle. Now, it is critical to remember that eventually the vehicle will still make it down the street. However, these barriers will slow down your defenders as well, normal users and your server. But no matter how high you build your barrier, an attacker will ultimately be able to overcome it. The ongoing challenges is to slow down attackers while balancing the needs and satisfaction of your users. Hash functions are also used for message authentication, which is a mechanism or service used to verify the integrity of a message. Message authentication assures that data received are exactly as sent, that is, contain no modification, insertion, deletion or replay. In many cases, there is a requirement that the authentication mechanism assures that purported identity of the sender is valid. When a hash function is used to provide message authentication, the hash function value is often referred to as a message digest. The most common hash functions used in digital forensics are message digest 5 or MD5 and secure hashing algorithm SHA-1 and 2. Message digest 5. The MD5 or message digest algorithm hashing algorithm is a one-way cryptographic function that accepts a message of any length as input and returns a fixed length digest value to be used for authenticating the original message as output. It was originally designed for use as a secure cryptographic hash algorithm for authenticating digital signatures. But MD5 has been deprecated for uses other than as non-cryptographic checksum to verify data integrity and detect unintentional data corruption. Uses of MD5. Although originally designed as a cryptographic message authentication code algorithm for use on the internet, it is no longer considered reliable for use as a cryptographic checksum because security experts have demonstrated techniques capable of easily producing MD5 collisions on commercial off-the-shelf computers. An encryption collision means two files have the same hash. Hash functions are used for message security, password security, computer forensics and cryptocurrency. Ronald Rivest, founder of RSA, designed MD5 in 1991 as an improvement to a prior message digest algorithm MD4. Describing it in Internet Engineering Task Force, that is IETF, request for comments RFC 1321, the MD5 message digest algorithm. He wrote, the algorithm takes as input a message of arbitrary length and produces as output a 128-bit fingerprint or message digest of the input. It is conjectured that it is computationally infeasible to produce two messages having the same message digest or to produce any message having a given pre-specified target message digest. The MD5 algorithm is intended for digital signature applications where a large file must be compressed in a secure manner before being encrypted with a private or secret key under a public key crypto system such as RSA. IETF suggests MD5 hashing can still be used for integrity protection, as the MD5 checksum is used in line with the protocol solely to protect against errors, and MD5 checksum is still an acceptable use. Characteristics of message digest algorithm. Message digests, also known as hash functions, are one-way functions. They accept a message of any size as input and produce as output a fixed length message digest. MD5 is the third message digest algorithm reverse created. MD2, MD4 and MD5 have similar structures, but MD2 was optimized for 8-bit machines in comparison with the two later algorithms, which are designed for 32-bit machines. The MD5 algorithm is an extension of MD4, which the critical review found to be fast but potentially insecure. In comparison, MD5 is not quite as fast as the MD4 algorithm, but offered much more assurance of data security. When considering the working of MD5, this hashing algorithm processes data in 512-bit strings broken down into 16 words composed of 32 bits each. The output from MD5 is a 128-bit message digest value. Computation of the MD5 digest value is performed in separate stages that process each 512-bit block of data along with the value computed in the preceding stage. The first stage begins with the message digest values initialized using consecutive hexadecimal numerical values. Each stage includes 4 message digest passes, which manipulate values in the current data block and values processed from the previous block. The final value computed from the last block becomes the MD5 digest for that block. To be considered cryptographically secure, the hash function should meet 2 requirements. In the first case, it is impossible for an attacker to generate a message matching a specific hash value. And the second point, it is impossible for an attacker to create 2 messages that produce the same hash value. MD5 hashes are no longer considered cryptographically secure methods and should not be used for cryptographic authentication according to IETF. In 2011, IETF published RFC 6151, updated security considerations for the MD5 message digest and the HMAC MD5 algorithms, which cited a number of recent attacks against MD5 hashes. It mentioned one that generated hash collisions in a minute or less on a standard notebook, and another that could generate a collision in as little as 10 seconds on a 2.6 GHz Pentium 4 system. As a result, IETF suggested that new protocol designs should not use MD5 at all, and that the recent research attacks against the algorithm have provided sufficient reason to eliminate MD5 usage in applications where collision resistance is required, such as digital signatures. Alternate hash codes to MD5 include Secure Hash Algorithm SHA-1 and SHA-2. Secure Hash Algorithm 1 SHA-1. SHA-1 was developed by the US government in the 1990s. This algorithm used techniques like those of MD5 in the design of message digest algorithms. But SHA-1 generated more secure 160-bit values when compared to MD5's 128-bit hash value length. In spite of this, SHA-1 had some weaknesses and did not prove to be the ultimate algorithmic methodology for encryption either. Security concerns began to emerge, promoting companies like Microsoft to discontinue support for SHA-1 in its software. The SHA-2 hash code family. The most secure successor to SHA-1 and one that is widely used today is the SHA-2 family of hash codes. SHA-2 hash codes were created by the US National Security Agency in 2001. They represent a significant departure from SHA-1 in that the SHA-2 message digest algorithms were longer and harder to break. The SHA-2 family of algorithms delivers hash values that are 224, 256, 384 and 512 bits in length. They are not by the names of their message digest length. For example, SHA-224 and SHA-256. The processing consists of the following steps. Step 1. Append padding bits. The message is padded so that its length is congruent to 896 modulo 1024. Padding is always added even if the message is already of the desired length. Thus, the number of padding bits is in the range of 1 to 1024. The padding consists of a single 1 bit followed by the necessary number of 0 bits. Step 2. Append length. A block of 128 bits is appended to the message. This block is treated as an unsigned 128-bit integer as the most significant byte first and contains the length of the original message before the padding. The outcome of the first two steps yields a message that is an integer multiple of 1024 bits in length. Hence, the expanded message is represented as the sequence of 1024-bit blocks M1, M2, etc. Mn, so that the total length of the expanded message is n into 1024 bits. Step 3. Initialize hash buffer. A 512-bit buffer is used to hold intermediate and final results of the hash function. The buffer can be represented as 8 64-bit registers A, B, C, D, E, F, G, H. These registers are initialized to 64-bit integers in hexadecimal values. These values are stored in big endian format, which is the most significant byte of a word in the low address, that is leftmost byte position. These words were obtained by taking the first 64 bits of the fractional parts of the square roots of the first 8 prime numbers. Step 4. Process messages in 1024-bit, that is 128 word blocks. The heart of the algorithm is a module that consists of 80 rounds. This module is labeled F in the figure shown. Each round takes as input the 512-bit buffer value A, B, C, D, E, F, G, H and updates the contents of the buffer. At input to the first round, the buffer has the value of the intermediate hash value Hi-1. Each round T makes use of a 64-bit value Wi derived from the current 1024-bit block being processed, that is Mi. These values are derived using a message schedule described subsequently. Each round also make use of an additive constant Kt, where 0 less than or equal to t less than or equal to 79 indicates one of the 80 rounds. These words represent the first 64 bits of the fractional parts of the cube roots of the first 80 prime numbers. The constants provide a randomized set of 64-bit patterns, which should eliminate any regularity in the input data. The output of the 80th round is added to the input to the first round Hi-1 to produce Hi. The addition is done independently for each of the 8 words in the buffer with each of the corresponding words in Hi-1 using addition modulo 2 raised to 64. Step 5. Output. After all n 1024-bit blocks have been processed, the output from the nth stage is the 512-bit message digest. While learning about cryptographic hash functions, you may come to know the term whirlpool. Whirlpool is a cryptographic hash function designed by Vincent Richmond and Paulo S.L.M. Barreto in 2000. It can be considered as a substantially modified advanced encryption standard or AES. Whirlpool takes a message of any length less than 2 raised to 256 bits and returns a 512-bit message digest. So, this module discusses the cryptographic hash functions as an attempt to safeguard the information we are exchanging through communication devices. Message authentication is one of the processes in which the integrity of the messages are ensured and secure hash algorithms are used to create the ciphertext in the form of message digest. The most commonly used algorithms in this category, such as MD5 and SHA, are examined in this module. Hope you understand the topics discussed here. See you next time. Bye.